So let's start the lecture. Give me a moment. Good evening, everyone. I'm Anand Singhal, PhD student from IT Jodhpur, and I'll be assisting in solving the problem from the course Digital Electronic Circuits, which is taught by Professor Gautam Saha at NPTEL, who is a professor from IIT Kharagpur, and I'll be assisting you in solving week 2 assignment problem that will be similar to the week 2 assignment problem, and they will help you in solving some of the assignment problem that you have been given to solve. So, as we discussed in the last lecture, there are some of the problems which were related to, as you can see. So, this is the course broad course outline, and we have already discussed that from week 1. Give me a moment again. That from week 1 to week 6, we will be covering most of the combinational circuit part, that is combinational. And from week 7 to till last week, we will be covering the sequential part of the course. So these are the basic two division of the course, and they are divided into several weeks. And in the week 1 itself, we have already covered the part which is introduction. The basic introduction. I have covered a lot of diode and transistor switches, and we have also covered the concept of noise margin, fan out, propagation delay, etc. And we also saw some of the problems that were theoretical and they were related to the transistor logic or the CMOS logic. And in this week, we'll be covering some of the logic gates, some of the universal gates such as NAND NOR gates, some of the implementations such as AND OR implementation, etc. And then we'll be covering some of the Boolean algebra axioms and basic theorems that we need to minimize or to save the energy consumption. Then we'll be doing some of the canonical representation, conversion of SOP and POS forms. There are several forms that we'll be studying, and at last we'll be ending the lecture with some of the problems which are related to K-maps and some of the don't care conditions. So this is the basic outline, and as I have already told you in the last class that the video lectures will be uploaded for every week, and I have already uploaded the lecture for week 1 at the NPTEL YouTube channel. That is, you can search the lecture in by search on YouTube. You can search this, and it will come. There is a channel in which every week a lecture will be uploaded. So I've already uploaded the week 1 lecture, and this week's lecture will also be uploaded timely. And this is how it will work. You can see the recordings on the YouTube, and you can see the PDFs of this lecture on the drive link which is provided by NPTEL itself to you. So there will be two things. One is this PDF drive, and one is this NPTEL lecture, which will be covered using. So yeah, you need to see the recordings in the YouTube channel. So let's proceed with some of the problems. So let's start with the first problem, which is a basic Boolean algebra problem. So we need to simplify a function f which is given. There is a certain function x which is given, and we need to get a simplified Boolean expression. So first of all, I need to tell some of the basic Boolean expressions. So let's start. So there are basic Boolean expression which are related to and OR operation. So I'll write all of them, maybe a times 1, a times 0, and you can write a plus a. There can be a plus 0, there can be a plus 1, etc., etc. So what is the basic relation? A basic relation is when you multiply a variable or when you do the AND operation of a variable with the variable itself, it will give you the variable again. If you multiply a variable with 1, that is high value, it will give you the variable again. If you multiply any variable, if you end any variable with a 0, so we know in the end truth table, if there is a single 0, then the output y is always 1. So if you multiply any variable with a 0, it will always give you a 0. If you add any variable, or if you give So yes, let's continue. So I was telling you some of the more properties which were related to the complement. So if we do the AND operation of a complement, then it will always give you a zero, because if there is a one, let's say there the complement of that will be zero. Even if there is a zero, the complement will be one. So we are anyway getting a zero. So as I said you, doing an AND operation with a zero with any variable will always give you a zero. Similarly, with the case with the OR operation, if we add the same, then it will give you one, because ultimately we will have one on either side. Then there can be, yes, I guess this will work. So let's see the question now. So the first part you can see here, if I write using it some with some different ink, this will be x dot x complement, which is similar to this property. If I denote it with a green ink, so I can clearly write this term as 0 and 0 addition with certain variable, which let's say this is p. I'm talking about this variable right now. So let's say this is p. So 0 addition with any variable, as you can see in this property, is the variable itself. So I'll write the variable now, which is left behind, which is xz x complement y plus z complement. So now I'll continue. I'll open the bracket again, which will be xz times x complement y plus xz z complement. Now again, I can rearrange this because they are all associative and communicative. So let's say I have this x complement y z, and this is x z z complement. So now you can see again there is one more twist, not twist, but one more basic thing to see here is x, and x is getting ended with x complement again, and here z is getting ended with z complement. So as we discussed, the complement, this part, that if you multiply a complement, it will always give you a zero. So I'm doing the same again. So 0 is getting multiplied by a certain variable, and here x is getting multiplied by a 0. So now getting to one of the properties, which is just adding or doing the AND operation with a variable itself will always give you 0, since in the AND operation, if we have a 0, it will, the output will always result in a 0. So I can write this as 0 plus 0, and we already know the OR operation, so 0 plus 0 will always give you a 0. So the final answer to this problem will be, let's see the problem, yeah, option A. So option A is the correct answer. We had a function and we had just minimized, or we have the simplified Boolean expression. So this is nullified by a 0. So even if you make this circuit, this will always give you a low logic. So there is no sense of making such circuit. So that is why minimization or simplification is very important. So just take a look, and then we'll proceed to the next problem in 2 minutes. Okay, so now let's proceed to the next problem. So this is a matching problem. As you can see, we need to solve certain columns and we need to match column 1 with column 2. So there are several rules. So first of all, there is something, like x plus y. There is something we need to compute x. Maybe we need to use the RHS to compute this x. Then there are several relations which we need to simplify that we did in the last problem itself. So we'll proceed with the same. So the first problem is x plus y. So there are several options here. First of all, I would like to add that they are both associative and commutative. That is, x plus y is equals to y plus x. It is the same thing. Then, so clearly for option A, for column 1 and row A, we have clearly the option as 2, which is present itself. Now for option B, we need to compute RHS. So first we'll see the answers for option C and D, and then we'll go back to the option B itself, which will be remaining. So for option C, which we can clearly see, the first term is x times x complement plus y, as you can clearly see here. Then we have for option D, we have a term x y plus x y complement. So we'll solve them one by one to get the final relation, and then we'll see if they are matching with the column 2. So I'm starting with C first. So it is x times x complement plus y. So again, if I open the bracket, it will be x times x complement plus xy. And we have just read that doing a AND operation with a variable will always result in a 0. So this is nothing but 0 getting OR with xy. So again, if I go back to the first question and see the property, so adding 0 to any variable will result in the variable itself. So what I can write here is the variable itself. So C is xy. So this particular term is getting shortened to xy. Now if I solve the same for D, let me use the red ink. So this is the D expression. So I'm writing it in the next page, that is xy plus, it was x and y getting odd with xy complement. So I can easily take x common from both of these, and this will be y plus y complement. So I have just gave you this property also in the first question itself. So let's go back. If adding any variable to the complement, that is, even if there is a 0, the complement will be 1. If there is a 1, the complement will be 0. So the you can say 1 is present in the add operation or the OR operation, so it will always result in a 1. That is what I already told you. So using the same property, what I can write is x is getting multiplied, or x is getting ended with 1. And multiplying any variable with a 1 will give you the variable back. So I've got D. For D, I've got a x, and for C, I've got a xy. So let's check. So for C, I've got a xy, which is option 1, or from column 2, it is row 1. So I can write this as 1. For option D, I've got x, that is option 3. So now what we need to check, if this particular expression is getting reduced to x or not. So the particular expression, if I can see, it is x plus y getting ended with x plus y complement. So I can write the same, and I'm just simplify. So this is third, which is x plus y complement. So I'll just try to solve it. So I'm opening the bracket one by one. So the first term will be x times x. The second term will be x times y complement. The third term will be x times y, and the fourth term will be y times y complement. So first of all, do the easier things first. We can clearly see the AND operation of a complement with a variable, so it will result in a 0, and 0 adding the to any term will again do a same thing. And this is a same variable with a variable, so let's say it will be a, and this will be a times a complement, which will be 0. So I'm just simplifying. I can write this as x plus xy complement plus xy. So you can clearly see there is a x common in all the terms, so I can write this as 1 plus y complement plus y. So there can be two properties that can be applied here. One is y complement plus y will give you a 1, that we have already discussed, and 1 plus 1 will be 1, the OR operation. Or you can, here you can write x 1 plus any variable p. It will again give you a 1, because adding 1 to any variable will always result in a 1. So either I can write x times 1, or using this property I can write 1 plus 1. So finally I'm getting x times 1, which is reducing it to x, which is fine for the second option, as we wanted to reduce this particular fourth column to B. So for B, fourth column. So the correct answer to this question is, if you can write in terms of ABCD, it is equivalent to 2413. I hope this problem is clear. So again, take a look. So we'll solve the next problem in 2 minutes. Okay, so let's proceed now to the next problem. So now this problem is particularly related to the Boolean function, which is represented in min term. So I'll tell you what is min term and max term, and using that and using the K map, we will solve this, or we'll simplify the Boolean expression. So there are several ways of representing Boolean expression or Boolean functions. So there are two particular ways to write. It can be either a min term or a max term. Let me use some dark ink. So in min terms, it is generally denoted by summation, and the max terms is generally denoted by pi. So this is a summation, so this is in the form of min terms. So I'll let you know what basically min terms are. So give me a moment. Yeah. So you can also say min terms can be called in the SOP form, and the max terms are POS form. Wow. Now what is SOP? SOP is sum of product. That is sum of certain products. So let's say I have a AB and I have a CD. So I'm doing a sum and I'm doing the product now. So this is why this is a sum of product form. And let's say I'm doing a sum first and doing the product later. So this is a product of sum form. So this is denoted by max term. This is you can call as max term, and this is you can call as min term. These are the basic difference here in the min terms and max term. And after that, min term, so let me make a truth table so that can be understood. So let's say I have a D final, so it is 0, 0, 0. So what in min terms, what happens is 0 is represented by a complement, whereas 1 is represented by a single variable. So let's say 0 is represented, if I say a variable A, so it will be represented by A complement, and 1 will be represented by A. So I'm doing the same here. So since you can see clearly A, B, C all are 0, so it will be A complement, B complement, and then C complement. Similarly for 0, 0, it will be A complement, B complement, C, A complement, B, C complement, and similarly A complement, B, C. Then I have A times B complement, C complement, similarly A, B complement, C. For 1, 0, 1 I have written. So here it is A, B, C complement. So basically wherever there is a 0, I'm just adding a complement. You can see here two complements. So this is how we represent the min terms, and we can make K-map using min terms. So here min terms are, if I write in the decimal value, so basically this is 0, 1, 2, 3. 4, 5, 6, 7. Now the given question has a min term of 3, something 3, 4, 6, 7 basically. So first of all, we can clearly or easily write the min terms as the addition of these four terms, that is this plus, then fourth, this plus, then I have a sixth, then this plus, and then this. But we always prefer to, what we prefer is to minimize the expression. So if I try to minimize the expression using the K-map, so we already know what a K-map is using the lectures. So let's try to make, oh sorry, so this, since this is 3 variables, so there will be 3, that will be 2 cross 4, that will be 8 possible values. So it will be A complement A, then using the gray code annotation, so we can write the same. The numbering is something like this: 0, 1, 2, 3, and 4, 5, 6, 7. Now we already know we need to simplify the Boolean expression. It is as it is clearly mentioned. So that is why we have not directly written the form. So I'll just fill it 3, 4, 6, 7. It will be 3, 4, and then 6, and then 7. So you can clearly see what we have is we have two pairs here, that will be this pair and this pair. So since all the ones are clear easily covered, so we don't need to take any additional pairs, such as some might take this first and then this first, and then again finally getting this. So you can clearly see this is a redundant pair, so we don't need to take this. So be aware of that. Please avoid the redundant pairs. So if I try to simplify it now, so let's say I have a final function which is f, which is in the form of x, y, z. Okay, so here I have written ABC. So first of all, I'll write the same in ABC terms. So it will be BC, that will be this, and then this will be giving me a and then a C complement. Now similarly, I have done it for ABC and doing it for X, Y, Z. BC will be replaced by YZ, and A will be replaced by X, and C is Z complement. So the final answer to this problem will be X Z complement plus YZ. So basically we can write 3, 4, 6, 7 as equivalent to this term, which is X Z complement plus YZ. So I hope this question is clear. So we have minimized this to X Z complement plus YZ, which is the final answer. So again, take a look. We will solve the next problem in 2 minutes. Okay, so let's proceed now. Now we have another problem, which is we need to simplify the following expression. Again, it is a simplification problem using the minimum number of letters required, and some of the given function is, let's say it is f, which is given by xy plus yz plus x complement z. So again, we can convert it into a standard canonical form, that is, it should contain, each and every variable should contain all the terms such as x, y, z, z bar, then y, z. We don't have a x here. Then ultimately we have x complement z, and we don't have a y here. That will give you all the main terms, and then we can fill the k-map, or we can fill the k-map directly also. So first, let's go with the conventional method. That is, the first term will be xyz. This will be xyz complement. The next term will be again xyz plus x complement z. Then I have a x complement yz, and finally I have x complement y complement z. So if I try to change the main terms, this will be 7, this will be 1 1 0, that will be 6, this will again be 7, this will be 0 1 1, that will be 3, this will be 0, this will be 0 1 1 again, that will be 3, and finally I have 0 0 1, that will be 1. So I can either fill k map by using 1 3 6 7, or I can fill the k map directly. So let's do the same. Again, we have 3 variables, so I need to make 2 cross 4 k map, that will be x complement x, y complement z complement, y complement z, y z, and then y z complement. No. So either I can fill 1 3 6 7, that will be 1 3 6 7, or I could have filled the k map using a shortcut, that is, if I go again, I can try to make the same. So let's say this is same. So now what we see is the given literal was xy plus yz plus x complement z. So x, y we need to fill. So we have a x here. So let's say I'm using a green ink. So there is a x, and you can see y is 1 for this and this particular columns. So if I do the intersection of them, so these are two are getting intersection. So I can write 1 1 here. Similarly for yz, I have y I have already intersected, and then z I have these two particular columns. Let's say these. So I only have this as an intersecting column for yz, and similarly for x complement z, I have a x like this, and z is these two. So again this. So this is how I can fill it using the shortcut itself. We don't need to convert it to a standard canonical form. That will do it easier. So now we need to make either quads or pairs. So let's do the same. So if I can make a pair here and pair here, everything will be covered. So the problem in this question was there was an additional redundant term that I also taught in the previous problem, that we should avoid these redundant terms to take, because it will basically result in not in simplification but in more computational power. So that is why we can easily reduce the given expression, that was xy plus yz plus x complement z, to these two terms, which are basically x y, which is this term xy, and this term is x complement and z. So basically yz was a redundant term in this particular expression, and the final answer will be xy plus x complement z. And yes, so you can write this as xy plus x complement z. So this is redundant. So I hope this problem is clear. So you can take a look, and we'll go to the next problem in 1 or 2 minutes. Let's move ahead now. Okay, so now the particular problem is a conversion problem. So conversion problem, basically we need to convert the, so you can see there are several bases. In this particular problem, it is 156 to the base 8. So base 8 is in the topic of number systems. We have several bases. We need to convert this base 8 problem. You have already covered in this in all of these in the theory lectures also by Professor Gautam Sir. So you need to convert the base 8 to base 16. So there can be two methods. So first will can be the conventional method, which in which what you will do is you will convert the same into its equivalent decimal form, and then doing the LCM part and all, you can convert it to the hexadecimal form. So let's follow the conventional form first, and then we'll proceed ahead with the shortcut form. So here we have a 156 to the base 8. So let's convert it to a decimal equivalent. So I can write this as 1 times 8 square, 5 times 8 raised to power 1, 5, and then 6 times 8 raised to power 0. So this is 64, this is 40, and then finally I have a 6. So this will add to 110. So basically to the base 8, 156 is 110 to the base 10. Now what I can do is I can take the LCM. For base 16 I can write 6. So this is 16, 6 are 96. So I can write 6 here, and the remainder I should write here. So the remainder left is uh, the remainder that is left is 14. So yeah, 14 is the remainder left. So now we already know in hexadecimal there is a representation from 0 to 15, and if from 0 to 9 we have the digit 0 to 9 itself, and for 10, 11, 12, 13, 14, 15 we have the denotions by A, B, C, D, E, and F. So here there is a 14, so it is denoted by E, as you can see. So the final expression, that is 110 to the base 10, is equivalent to 6E to the base 16, and this is equivalent to again the question, which is 156 to the base 8. This is the conventional solution. This is how you can proceed for this particular problem using the conventional methods. And then if you try to proceed with a shortcut method, so let's try that also. As I said, you need to convert the same problem to its binary equivalent first. So this is 156 to the base 8. So what you can do is you can do the binary directly. So you can write each of them is as the binary equivalent in 3 bytes, since we have a 8 denotion. So 1 you can write as 001, then 5 you can write as 101. In a pair of 3, basically I'm writing at 110. So 101. So this is the binary representation of the any octal number. And from binary to hexadecimal, what you can do is you can make a pair of 4 instead of. So let me rewrite this. I can write this as 001, 101, and then 110. So from starting from right, you can make a pair of 4s for hexadecimal. So this is first, then this is second, and if you are left with anything, just add more zeros. So you can write this as equivalently as 0, and this is 0110, which is getting reduced to 6, and then this is 1110, which is equivalent to 14, and 14 in hexadecimal is E. So you can write, you can see there is a shortcut now. We have easily calculated this as 6E16. So again, 156 to the base 8 is equal to 110 to the base 2, and then again to 16. And if I can write the binary also to completely solve the problem, it is 101, 110 to the base 2. So I hope this clears any of the doubts. So you can again see. So this was the conventional method. I've converted it to decimal and then gone with the decimal to hexadecimal again, conversion using the LCM, and then finally using the shortcut from binary, and then from binary to hexadecimal, we have easily calculated the hexadecimal. So take a look and we'll start the problem in 2 minutes. So let's proceed to the next problem now. So we have a problem which is giving a certain circuit, and we need to solve the dual expression. So we have a concept of dual in this particular problem. We need to find the dual of the output D. So here is D, here is E, and here are ABC, which are inputs. So let's first of all see. So there are several gates. So this is XOR gate, as you can see the denotation. This is NOT, this is AND. Then I have XOR again. I have a NOT here. I have a AND gate here, and then ultimately I have a OR gate here. So as you can see, A is getting inputted to this, and here it is BC. So this will be B XOR C. Here it will be B complement. Here it will be C. So this will be B C complement, and finally this is getting into the NOT. So this will be B XNOR C, and this is A. So these are getting ended. A times B XNOR C, and this is basically A XOR B XOR C. So I can write the final expressions clearly. For D it is A XOR B XOR C, and for E it is A B XOR C plus B C complement. So just I have solved the expression E. It doesn't even we does not even require to solve this E, but for the sanity check I have given E expression. So now the problem says we need to find the dual expression of output D. So I have a D. I need to find the dual expression. So I hope you know that in the K map, if I may try to make, let's say, if I make a truth table and this is D. So for XOR operation, we already know that when we have even, oh sorry, when we have odd numbers of 1, the output is 1. So I can write this as 0, then I can write this as 1, 1. Then we have a 0, then we have a 1, 0, 0, 1. So I can clearly see that in the minterms format, what I have is, I have a 1, I have a 2, I have a 4, and I have a 7. So I can write this in the form of minterm as 1, 2, 4, 7. And now a good thing is a dual is basically the replacement of AND circuit with a OR, that is a dot with a plus and a plus with a dot. Basically AND OR with a AND, or any complement with a direct. So basically the dual of minterm is the max terms itself. And there is one more thing that I need to add here is, that is a self dual. Let's say I have a function f which is some function of x, y, z. Then I calculate the dual of that. That will again be a function of some x, y, z. And let's say this is g. So if f is equivalent to g, then f and g, or f and g are self duals. So basically what I have written here is a minterm, the dual will be max term. So I can write this as max term. Whatever left is there, so 0, 3, 5, 6. Now the good thing about the XNOR function is, the XNOR function is a self dual. So if you calculate the XOR using the K map and you try to do the max terms, so the thing that will be left are the min terms only. So basically A XOR B XOR C is a self dual. So what you can write is the XOR function, that is 1, 2, 4, 7 is a self dual. So let's write it in the form of the option. So we have a elaborated form. So let's write summation 1, 2, 4, 7 will give me, one is A complement B complement C, and I have a 2 that will be 0, 1, 0, and I have a 4 which will be 1, 0, 0, and then I have a 7 which will be 1, 1, 1. So let's check the options now. So in this option C I have a 1, 1, 1, that will be 7. In option 1C I have 0, 0, 0, and I have 1, 1, 0, 1, it will be 5. So this is wrong because already 0 and 5 is there. So let's check with other options. Let's say option A, it will be 7, and I have a 0, so this is also wrong. I have a 7 in option D, and then 0 1 0, that will be 2, and then I have a 1 0 0, that will be 4, but in the final part I have 5, so this is also wrong. So let's check option B now. So I have a 7, then I have 0 1 0, that will be 2, and I have 1 0 0, that will be 4, and finally I have 0 0 1, that will be 1. So yeah, option B is the correct answer. So dual, it is a self-dual function basically. So dual for the same will be 1 2 4 7 in the min terms itself. So let's just check it out, and then we'll solve the next problem in 2 minutes. So let's start with the next question now. Give me a moment. Yes, so our next question deals with. So we have already covered what is SOP and POS form as in the previous questions. Now there is a particular POS form in which we want to convert it to a SOP form. So we have just got the idea that if we know the max terms, then we can find the min terms easily using the corresponding max terms, because since they are duals basically, so the given max terms, so whatever has been left will be the min terms. So using this shortcut, we'll try to do this question since we have a standard form. So it is given a plus b plus c times. So this is a POS form. A plus b complement plus c complement. And in max terms, what happens is 0 is represented by the variable and 1 is represented by the complement of that variable. So I can write this as 0 0 0 basically, and I can write this as 0 1 1. So I can clearly see this is 0 and this is 3. So I can write the particular expression as max terms 0 3, which will be equivalent to the min terms of the rest of the terms, that is 1 2 0 and 3 are already covered, so it will be 4 5 6 7. So we just need to see 1 2 3 4 5 6. So all of them has 6 terms, so we just need to see what is the max term, sorry, what is the min term. So we'll see that. So if I just add a page, so 1 is again 0 0 1, 2 is 0 1 0, 4 is 1 0 0, 5 is 1 0 1, 6 is 1 1 0, and 7 is A B C. So we just need to check the options. So this is quite straight. So let's check what is this 1 2 4 5 6 7. So 1 is here, 1 is here. Then we have 0 1 1. So this will be 3. So 3, is it possible? No, 3 is not possible. So let's check option C then. So it is 0 0 1. So 1 is there. It is 0 1 0. So 2 is there. It is 0. It is 1 0 0. So 4 is there. Then 101. So 5 is there. Then 110. That is 6 and 7. Yeah. So option C is the correct answer. I hope this concept is clear. So let's move quickly now to the next question, which is again okay. So now as we already discussed what is self-dual, so we just need to find the self-dual. So particularly there are two particular functions which are given in the options. One is a XOR b XOR c, which we just checked is nothing but 1 2 4 7, and there is one more function which is given in the question, which is ab plus bc plus ca, which is also known as three input majority function. Why majority? Because this gives the function output 1 when more ones are 0 in the input. So I'll make the truth table, and this is equivalent to summation min terms of 3 5 6 7. So let me quickly draw this 3 5 6 7. So let me make a truth table quickly. Let's say this is, so whenever there are more ones, so this is the case for 3, this is the case for 5 6 and 7. So it will be 1 for these three occasions, and whenever we will solve the same using the main terms, it will come out to be 3 5 6 7, as you can see. So the duals will be this function will be dual with this 3 5 6 7, and the XOR is a dual with 1 2 4 7. So let's check the option. So 3 5 6 7 is given as a dual with XOR, so this is wrong. Then AB plus BC plus CA is 3 5 6 7, but it is given 1 2 3 4. Then we have 0 1 5 7, which is nothing, no combination, and we have a 1 2 4 7, which is XOR. So option C will be the correct answer. I hope it is clear because it was quite easy. Now let's move to the to the next question. So in this question particularly, this is a binary, this is a expression question. So it is said that f1 is given as a and fn is given as fn minus 1 times complement plus a. So basically what it is trying to say is f2 is f1 complement plus a. Similarly, f3 is f2 complement plus a. So now the question says we need to find the output when n is odd. So there must be a pattern that this question is following. So we'll see. So f1 is already given as a, f2 will be f1 complement plus a. So f1 complement will be a complement plus a, and this will be 1 by the property as we have already seen in the previous question. Now similarly, I'll calculate f3, that will be f2 complement plus a. That is, that will be 1 complement, which will be 0 plus a. So 0 plus a will give me a. Similarly, f4 will be f3 complement plus a. f3 we have just calculated a, so f3 complement will be a complement, so 1. So similarly, you can see there is a pattern, so it is coming out to be a1 a1. So we just need to check for even and odd integers. So let me write, as I can see, f1 f3 f5 so on. For f odd, it is coming out to be a, not 1, And for f2, f4, and so on, that is for n is equals to even, it is coming out to be 1. So we can write this fn function as a when n is odd and 1 when n is even. I hope you understand. This is very easy and this is a basic question. So the the question is asked for odd number. So we have just got the relation when it is odd. So fn is a. So option C is the correct answer. In fact, you can try the same question. Let's say if I give you fn is equals to fn in minus 1 complement plus a. So if I say that when n is even, so you would have got the answer as option B, that will be 1. Similarly, I can give you a relation such that fn minus 1 complement plus a complement, and similarly you need to find when n is odd, when n is even, what will be fn. So there can be multiple questions. So this is very good question to understand the concept of the binary part. So I hope this particular question is clear, and since this is very easy, so now we'll wait for 2 minutes and then proceed to the next question. Okay, so I'm getting mixed answers again. So let's just make a K map. Okay, so let's just fill the same. So this is 2, 3, 4, 5. Then I've got don't care at 10, 11, 12, which is here 13 also, then 14, 15. So in don't care, we just need to fill out once using the best combination. So what I can see is I have one as this quad, and this one will be covered by this. There are only two quads. That will be the first is giving B C complement, and the second is giving C B complement. So yeah, this is basically simple. B XOR C. So option B is correct. Let's see the options. I hope is it fine because some of you have written A. So I hope this is clear. Any doubts
Yes,
here?
sir.
Okay, okay. So try to do this question. Maybe take 2 3 minutes and let me know the answer. Okay, so I got one answer as C. We'll check in 1 or 2 minutes. Let me get some more answers. Okay, so let's check the same. So in the question it says if the input to the digital circuit is a cascade of 20 XOR gates. So there these are XOR gates and we have 20 XOR gates, and the input given is to all the XOR gates is this X. Find the value of output Y, which is this. Sorry. This is the first part. If the same question consists of 19, what will be the output Y? So basically this is again odd even. The pattern must be repeating. So again we need to have certain properties in our mind that we already discussed. Something like this. So in XOR we can have certain combinations which is this. So one by one let me know what is the answer to each and every one. So X XOR 1, what will be the answer? Again, if I try A XOR B to write the expression, this is A B complement plus B, sorry, A complement B. So I can write X complement 1 as X 1 complement plus X complement 1. So what will be the answer? Sorry.
X complement.
Similarly for X XOR X complement, what will be the answer? Can anyone tell quickly? I already told you these properties in the first.
One.
Yeah. For this X XOR X, okay, maybe you can check. So in the same question, I have a X here. So X XOR 1. So here it is X XOR 1 is, sorry, X complement again. And then we have a X. So X complement X XOR X complement is 1. So this is repeating. Okay. So maybe I can use. So if I have one XOR gate, my output is X complement. If I have two XOR gates, my output is 1. If I again have three XOR gates, my output will be, so I can write this as output will be X complement because it will be X XOR 1, which will be again X complement. Do you understand this? Any doubts in
Sir,
this? Okay, so for odd XOR gates, you can clearly see my output. Maybe I can denote this as Y. For odd XOR gates, the output will be X complement, and for even XOR gates, the output will always be 1. So in the first question, the XOR gates was 20, which is even. So for the first part, the first will be 1, and the second part will be X complement. Okay, and option C. Yeah, option C will be the correct answer. Any doubts in this?
no sir.
Okay, so just let me know the same answer if I replace this XOR by XNOR gates. Quickly let me know what will be the answer. The question remains same, just XOR gates are getting replaced by XNOR. You can take 2 minutes and let me know the answer. Similarly in the question also, it is XNOR. Again, these properties will help and give me the answer quickly.
One and X.
So I'm getting 1 and X. So again we can see here, wait. So if I am having a x here and a 1 here, so this will be x naught now. So just I'm replacing these with x naught with the purple ink. So x naught 1 will be, the relation will be x naught is a complement b complement. So this will be x into 1, which will be x. This will be replaced by x, then x complement. So this is 0, this will be 1, and this will be x complement. So 1 and x will have a x here, then x times x will have a 1 here. Then again 1 and x will have a x there. So yeah, x1 it will repeat. So for even it will be 1, and for odd it will be x. I guess this was the answer only. So 1 and x will be the final answer if XNOR was used instead of XOR here. So let's move ahead. Maybe, yeah. So just try this question out. Okay, wait. Is my screen visible? Hope there is some
No, sir.
glitch. Okay, wait. Is my screen visible now?
Yes, sir. Yes.
Okay, fine. Then try this question out. We can take 1-2 minutes. So I've got one answer is C. We'll check. I'll wait for some more answers and then I'll solve. Yes, I've got one more answer is B. Okay, so let's check now. I've given I've been given a K map in which X represent don't care, assume inputs are A, B, C, D, and also A complement, B complement, C complement are also available. We need to find the number of gates if the logic is implemented using two input NOR gates. NOR gate is basically X, Y, and it is X plus Y whole complement or X dot Y, X complement dot Y complement. So, what are the number of quads or pairs you are getting in this? Anyone?
Only one pair, sir.
Uh, you're saying only one pair,
Sorry, quad.
Quad, quad. One quad.
one quad. So, one quad, right? That quad will be here. We don't need to see the don't care. So, if this is the case, I can write this as this will be C, and this will be A complement. So, this particular K map, or let's say the function is F, it is getting to A complement C. And now you need to implement the same using a two input NOR gate, and all everything is available as an input A complement, B complement. You need to use NOR gate to get the output as A complement C. Some of you are saying it requires two, and some of you are saying it requires three also. So again, if I repeat, let's say if I had a A and a C here, what will be the output? Let's say G is that output. Anyone can tell what will be the G if A and C is here?
A plus C whole complement.
That will be A complement or C complement, right?
Sir, it is telling NOR gate.
Sorry.
NOR gate.
Yeah, so NOR gate, what is NOR? NOR is or getting complemented, right? X plus Y whole complement is X complement dot y, and Y complement, right? That is what I have written. Any doubts in this?
No.
No, no.
So if I give, since all the complements are also available, if I give A here and C complement here, what will be the output? Let's say F is that. Anyone, what will be the output now?
A bar C.
A bar C. That is my function, right? What will be the answer?
Sir, option C is the answer.
Why option C is the answer? Can you please explain why are you saying that three NOR gates are required to get the same?
Okay, okay. One NOR gate. I just did not get out.
So you can see that only one NOR gate is giving the final expression what I need. Everyone is able to understand the same?
If
Sir, I
inverter
did
inputs
that
are not
not
available, how many
express.
gates?
Okay, so if inverters are not available, then I will require to complement
Two.
this. I'll require one
Two.
more additional gate. So then it will be two.
Okay. Clear.
Yeah. So I hope it is clear to everyone. It will be option A. Uh, Still some are saying option B. So is there any doubt? Why option B?
I thought for inverter also I need one more NOR gate.
Yeah, I get it. Someone else has written just now that option B. Any doubts in option A is the correct option? If the question says that the complements are available, so don't need to have another inverter, another NOT gate for the inverter because it is available as an input. The question says that the complements are available. That is why one NOR gate is the answer. Is it fine?
Sir, are you trying to say that complements are also available in input?
Yes, I can directly use C complement here because the question says all the inputs and the respective complements are also available.
Sir,
Wherever it,
if the complements were not available, then
then
the answer
then
would be three Norgets now.
then the answer would be 2 by 3. Please explain why you're saying then 3 NOR gates are can be used. Let me make a circuit. Let's say I'm making this is C, this is A, this is F. What will be F here?
A bar C.
That is the required expression, right? Why are you saying 3 NOT gates? Can you explain what is the confusion?
No, sir, I did two not gates.
2 NOR gates if the complement is not available, and since the question is saying it is available, so the correct answer for this will be 1 NOR gate only. Is it fine now?
Yeah, it's fine.
Okay, fine. So let's move ahead. Try this question out and let me know the answer. Any answer for this? Okay, yes. So for the previous question, yeah, it is fine. If complements are available, then only one OR gate is required. That is what I answered. That option A is correct.
A answer, y is equivalent to 1.
Okay, so let's check it out. So the hint is given that you can verify using K-map minimization. So I'll try to simplify it. Y is a plus b times some expression which I am replacing by x for now. Then there is a complement b complement, and then so for that expression it is a complement b complement plus c complement, then whole complement. So I can write this as a plus b c. Yes, and a plus bc is also, if you know the property, it is a plus b a plus c. So if I just replace that, y is a plus b a plus c, and that is again a plus bc, and then the rest of the terms which are a complement b complement plus a complement c complement. So we can quickly make a k map to fill these terms. This is a. First term is a, so 1 will always be in this column. Then there is bc, so we have a 1 here. Then we have a complement b complement, so here and here there will be 1. And finally we have a complement and c complement. So all the terms are 1 here, so y will be 1 itself. Is it fine? This was simple, I guess. Is there any doubt in this? How I filled the K map and all? Any doubts here?
No.
Okay. Similarly, let's try to do this. Maybe you can take 1 or 2 minutes. Okay, so I'm getting some answers. One is B. So anyone else? You solve it in 1 or 2 minutes. Anyone else with any answer? So I've got missed answer. Mm, I've got B. Okay, wait. And I've got C. What else? So let's check. So in the given question, it says that x is 1. And then what we need to do? Then we need to calculate what is y or what is z basically. So if x is 1, you can clearly see the first term will be 1 plus something, a long variable. I'm replacing that by p, and then I'm getting x complement plus z complement x plus y. This is 1. So I can clearly neglect this term because it is 1 plus something. So I've left with now, since x is 1, I can write this as 0 plus z complement 0 plus, sorry, this will be 1 plus y. This will be again 1, and 1 plus anything will again be neglected. So z complement is 1, which will give me a z as 0. So yeah, C will be correct. Okay, y z complement. Is there any doubt in this? Someone has given the answer is B or even A. I've got all the options as the answers. So maybe I can uh, repeat the answer. So it says x is 1 in the given question. So 1, if I can write 1 here, 1 plus anything will be 1 only. So I've neglected this term. I'm only getting this term now, which will be 0 since it is x complement times z plus 1 plus y, and 1 plus anything I am again neglecting, which will give me z complement as 1. Any doubts here? Those who have given the answer as A and B? Is it clear?
Clear.
Okay, and what someone else has also given B. I hope it is clear, right?
Yes, sir, it's clear.
Okay, fine. So let's proceed now. So now the next question says find the minimum number of NAND gates required to realize expression AB plus CD. So now we are starting the topic of AND or implementation basically. Maybe you can try the same question. You can take 2-3 minutes and let me know the answer. Maybe I can give you the options 2, 3, 4. Sorry, this is third option, and then 5. Try it out and let me know what are you getting. Or you can write these as A, B, C, D. Maybe you can take 2-3 minutes and let me know. So I've already got the answer as 3. So let's wait for some more answers and then we'll check. Okay, so I've got two answers as 3. Okay, so there is a concept here which is AND or implementation. AND or implementation is basically equivalent to SOP implementation, that is sum of product. So whenever you are given a question in which you are getting a question in the form of sum of product, then it is very easier to implement the same using any NAND gates. So let me try to explain what I am trying to say. So the given circuit is AB plus CD. So if I try to make AB plus CD, sorry again, this will be AND first. AB plus CD, and I'll get this Y as AB plus CD. So why do we call it AND or implementation? If I cut this circuit, here there is a AND implementation, here there is a OR, which leads to this AND or implementation. or I can say the same as SOP implementation basically. Do you understand this part, everyone? Any doubts here? Anyone having any doubts till now? Okay, so I hope not. So now the shortcut doing the AND or implementation, why I said that using the SOP implementation you can make any circuit easily using a NAND gate is, if I just mm, first of all let me know if I have two NOT gates in series, and if I give input A, what will be the output Y? A only, right? So what I am doing is I'm using two NOT gates in series in this circuit directly. So you can see this has become a NAND gate, this has become a NAND gate, and this gates look something like inverted inputs. If I say AB is the input, so what will be the output here? Can anyone tell? Yes,
A plus B.
A complement plus B complement, because I have used the inverted, that is the NOT gate. And I can write this as AB whole complement, and this is nothing but a NAND gate, equivalent to a NAND gate. You understand this concept?
Yes.
Okay, so I have made this circuit that is for AB plus CD. If I make something like this is ABCD, this Y will be AB plus CD. So the correct answer for this question will be 3 only. You need to have minimum 3 NAND gates. Basically, if I write 2 input NAND gates, that will be more clear to realize this expression. So now, first of all, let me know if I give you a question AB plus CD, maybe you can take it as a homework problem for the next week, plus EF. The question is find the minimum number of NAND gates used to realize this expression. The first is you can use any number of inputs in the NAND gate, and second is you can only use two input NAND gates. So we'll start the next week with this. We will start the next week with this problem,
Sir,
and
any number means how much is the maximum?
I mean you can use three input, three output, whatever. Sorry, not output. You can use three input. Yeah, let's say not any number. You can even use three inputs for the first part, and for the second part you can use only two input NAND gates. So we'll start the problem, this problem in the next week's lecture as a first problem, and then we'll proceed to the subsequent topics. And again, if you have any doubts, you can mail me always. This is my mail ID. And again, there's a YouTube channel which is again similar. You can search this, you will find the YouTube channel. The recording will be uploaded in this particular YouTube channel, and then there is a drive in which this PDF will be uploaded. I guess the link will be shared by NPTEL itself. So we can dismiss the class for now for this week. Do you have any doubts? Any doubts, anyone?
No, sir.
Okay, then we shall meet in the next week at the same time. So thank you everyone for joining the class.
Thank you.
Thank you.